optimizations. Today, again, we are very honored to have Dr. James Saunderson from National University to continue to give us the lectures on polynomial optimizations. I'm sure that those who have attended the previous two lectures will agree with me that the lectures are fantastic, and indeed I personally learned a lot from that. So if I am correct, today James is going to probably give us a taste on the latest development on this exciting area. So without further ado, I'm going to hand over to James for his lecture. So now the stage is yours. So
great,
please,
thank you
James.
very much, Goy, and thanks for the introduction. Yes, so just, you're right. I'm just going to start with a very quick recap, and then we'll kind of dive into today's. I think we've got the die-hard audience of people who are, have been here the last few days. I think most people, but I think it's helpful to do a quick recap. So what have we seen? We've started with this family of polynomial optimization problems, and this kind of more general class of conic optimization problems with respect to non-negative polynomials. And we've seen that, certainly the question of getting global bounds on polynomial optimization problems can be reformulated as one of these conic optimization problems with respect to non-negative polynomials. Of course, the challenge with this latter class of problems is that the interesting constraint, the cone of polynomials non-negative over some set, is very difficult to work with. And what we saw in yesterday's talk was kind of a really systematic kind of approach to approximate non-negative polynomials on a set, and hence to approximate these conic optimization problems with respect to non-negative polynomials. In particular, what we saw is that we kind of have a bunch of parameters, in particular kind of degrees, sort of bounds on the degrees of the polynomials we're going to use. And once we choose these degree bounds, we can our systematic approaches to approximating really involve linear constraints on sums of squares of some degree. Okay, and we can then convert these things into semi-definite programs. All right, so that was the kind of the basic path. In practice, these semi-definite programs get very big unless the degree bounds are fairly small. But in principle, we have a really kind of coherent principled approach to approximating these problems, and the kind of theory about these things converging and so on is really based on fairly deep results about certifying infeasibility of systems of polynomial equations and inequalities. Okay, so today it's going to have kind of two parts. So a first part where we really go to a couple more examples, revisit some in light of what we've done, some really classical examples that I wanted to just talk through in a little bit more detail. And then in the second half of today's talk, maybe a little bit more than a half, I'm going to give a completely biased biased in the sense of it's biased towards things I'm aware of and I know about, of some recent research topics in the broad area of polynomials optimization and sums of squares and so on. Okay, it's by no means exhaustive. There's a number of different communities who are really using these tools and developing them in different ways, and so it's kind of extremely hard to keep track of what's going on. But also, so we'll see a smattering of things, but it's by no means representative. But hopefully, something there piques your interest. Okay, so some more examples. So let's go back to our example of stability of polynomial vector fields that we saw in the very first lecture. And I just want to kind of recap this and connect this back to our sum of squares tools. All right. So what was the setup? I start with a polynomial vector field. So for example, the one on the bottom left is a vector field with two variables. It's a cubic vector field with two variables. Okay, and we want to establish that the origin is globally asymptotically stable equilibrium point, which one way to do this is to find an energy-like function that is positive everywhere except at the equilibrium point of interest. Okay, and it has the property that whenever you start your system and you evolve the differential equation, you integrate the differential equation, the function decreases strictly along trajectory. So we call this often a Lyapunov function. And this is the setup here for continuous time dynamical systems. There's a comparable setup for discrete time dynamical systems. And just to sort of put it out there, any kind of iterative algorithm, is an example of a discrete time dynamical system. And so people have also used these ideas of coming up with Lyapunov functions for discrete time dynamical systems as ways to, for example, analyze iterative algorithms for optimization. So there's kind of really interesting connections between analysis of algorithms and this kind of stability, particularly in the discrete time setting of vector fields. Okay, so this is the setup. Now we know what we know. Okay, so we know that we can prove stability by finding such a function. Okay, and so what's the idea is that we're going to restrict to polynomial functions of some degree, and we can certify stability, for example, by finding a V, okay, that is where that's, not just, I mean, before we wanted a V that was positive definite. Here we could ask for something stronger in two ways. Okay, we could ask for something that's not just a sum of squares, okay, but in fact, even when you take a little bit off it, it's a sum of squares. So this, what I've done here enforces being positive definite. There's other ways to do this, but this is one sort of simple way to make it positive definite, not just non-negative. Okay, but in here we've also replaced non-negativity with sums of squares. Okay, and similarly we can do the same thing. If you look at this time derivative of v along x of t, okay, using the chain rule, this comes down, oops, there's a typo here, to negative inner product of the gradient and the vector field. We want that to be a sum of squares. And to make this strictly negative, I should have a minus sign here in front of the epsilon, again, using a similar technique. Okay, so this is how you formulate these things. Okay, and for example, if we were to try to do this on our vector field in the example, it turns out you can find a degree 6 of the Lyapunov function, that satisfies these constraints. Notice that the second one here, we have things of degree 8 because the vector field has degree 3. Okay, and the gradient of a polynomial of degree 6 has degree 5. So this overall expression will have degree 8. Okay, so it turns out that a degree 6 function, the level sets of which are shown here in red, all right, will certify stability of this equilibrium point using sum of squares based techniques. Okay, so that's nice. I do want to warn you that there are interesting examples that show that you can have a globally asymptotically stable polynomial vector field that has no polynomial Lyapunov function, let alone a sum of squares type Lyapunov function. Okay, so these techniques don't always work, at least in the case of inhomogeneous vector fields. Okay, but they work in a lot of useful situations, and they're really one of the becoming a standard tool to sort of analyze at least low-dimensional nonlinear dynamical systems. Okay, so that's just kind of to kind of close the loop on how you would actually go about using the tools we've developed to try to certify stability of these sort of nonlinear dynamical systems. All right, so let's go to a different example, one that looks kind of scary at first sight if you've never seen these kinds of things before. And it's an example that really comes from kind of quantum systems, quantum information theory in particular. Okay, and there's a whole lot of physics and stuff behind this that I can't comment on because I don't understand. I don't understand the interpretations of the physics and so on. But the mathematical interpretation I'll try to give you of this setup. Okay, so in this world, we think of a system as being, say, a vector space of some dimension, and a state, a quantum state on the system in this formalism is just going to be a PSD matrix with trace 1. Okay, and so one sort of analog to think about is that if you have a diagonal PSD matrix with trace 1, okay, that's really just a bunch of non-negative numbers that sum up to 1, which we think of as a classical probability distribution. And this kind of PSD matrix with trace 1 is sort of our quantum analog of a probability distribution on this space. Okay, so that's some kind of way we could think about this formalism. All right. And then you could have then two systems, okay, system A and system B. Okay, we think about the joint system as like the tensor product of these two spaces. Okay, so it's an NA times NB dimensional space overall. All right. And again, if you think about the classical probability setting, the right analog is to think about two random variables that take finitely many values. Okay, one with some distribution P1 up to Pn, the other one with some distribution Q1 up to Qm, say. And what's the natural notion of being independent? Well, that's a joint distribution, okay, where the probabilities are just the pairwise products, right? So the probability of system 1 being in state I, system 2 being in state J is just Pi times Qj. Okay, so what's the quantum analog of this? Is that if you a sort of a natural sense of being independent, or in particular separable, it's called here, is that if you have a state on on system A and a state on system B. Okay, states on the joint system are states on the tensor product space. And if you take really the Kronecker product of the two density matrices, the state on the two systems, so each one is a PSD matrix, take the Kronecker product, that's kind of like, or that is the natural matrix analog of taking, two independent random variables and considering the joint distribution. Okay, so separable states are mathematically, they're defined to be just convex combinations. All right, so the P's are just some mixture, convex combinations of, if you like, Kronecker products of rank 1 matrices xi transpose, yi transpose. Right, and you should think of these as really coming from the eigen decomposition of two density matrices. Right, so you could just take this as the definition of something of interest in quantum information. Here's a convex set. Okay, so it's a set of all convex combinations of things of this form. All right, and we may or may not want to think about the x's and the y's as being normalized to have unit length. It's sort of not super important for what we're going to talk about. Okay, so this is some crazy convex set that people are interested in this setting. So that's what separable states are. And entangled states are all the other things that are not separable. And it's not completely obvious that there are such things. Okay, but so these are going to be NA-NB times NA-NB, so big PSD matrices with trace 1, okay, that cannot be expressed as convex combinations of these things of this form, okay? So the formula, that's the definition. And this is the same entanglement that you might have heard about when people talk about, quantum systems and weird things they do. I don't know what any of that means, but okay, this is the same idea, okay? And so the question is then, if you give me a state, so you give me an NA-NB times NA-NB PSD matrix with trace 1, how can I decide whether it's entangled or not? Okay, so it's kind of turns out to be a hard question. All right, but there's one approach we can take using the tools that we've got. Okay, so what have we seen? We've seen that separable states is a convex set, and the extreme points are or extreme rays, if we don't normalize, are of this kind of form. Okay, all the extreme points here. So because of convexity, okay, if I've got a convex set and I want to check that something's not in a convex set, okay, kind of general convexity theory tells me the way to do that is to find a hyperplane that separates my point, okay, from my convex set of separable states, okay? So to find a hyperplane, I need to think about what linear functionals mean on this space. So they define hyperplanes. So a linear functional on one of these bipartite states, I'm indexing this by, the NA times NB indices for the rows and the NA times NB indices for the columns. Okay, so what does a linear functional look like? Well, okay, it's some linear combination of these entries of this density matrix. But because of the symmetry in this density matrix, okay, you can interpret such a linear functional actually as the coefficients of a particular kind of polynomial with a particular symmetry structure. So you can interpret a linear functional on this space as really the coefficients of a biquadratic form. So what is a biquadratic form? Okay, it's a homogeneous polynomial of degree 4 that's homogeneous of degree 2 in the x variables, in some set of variables, and homogeneous of degree 2 in some other set of variables. Okay, and you can see that structure here. If you think about the entries of this this object, right, that consists of all the products of xi's and xj's and all the products of yi's and yj's, and every kind of monomial will have 2 x's and 2 y's. So this makes it biquadratic. All right, so it turns out that, okay, what are the supporting hyperplanes for the hyperplanes that exactly support this convex set of separable states? They're exactly the non-negative biquadratic forms. Okay, so non-negative polynomials of degree 4 that are homogeneous of degree 2 in each of 2 sets of variables. Okay, so in principle, if you give me some state, some big density matrix, I could decide whether it's entangled or not by searching to see if there's a biquadratic form, okay, whose coefficient sort of matrix or reasonably rearranged, okay, has negative inner product with my state, all right? So it will have necessarily non-negative inner product with all separable states, And if I can find one with negative inner product with my state, then I've witnessed the entanglement of this state. Okay, so this is kind of the formalism, the convex geometry. And then of course, we can apply the sum of squares machinery. And this has, been done a while ago, although there's been, much more recent work on understanding better this hierarchy. Okay, so what's this DPS for Doherty, Perillo, and Spedalieri hierarchy? Okay, again, I'm given a bipartite state, and now I want to use sum of squares ideas to try to certify that it's entangled. Okay, so what do I want to do? I want to find coefficients of a biquadratic form so that, for example, if you take, the inner product with, the inner product with my state sigma, I get -1, so something negative. The scaling means I can scale that to -1. And, I wanted this biquadratic form to be non-negative. Okay, but I'm going to ask instead for it to be a sum of squares when potentially multiplied by some multiplier. Okay, all right. And so, one of the main results of this paper, the DPS paper, is that in fact, if you give me any entangled state and I choose a large enough degree D, then, this expression will be a sum of squares, and I will be able to certify its entanglement by solving this feasibility problem, which is a semi-definite programming feasibility problem. Okay, it's not completely, this is a little bit subtle because notice that that the multipliers are only in one of the two sets of variables. It's not so obvious that you can do that, but you can by an extension of this uniform multipliers theorem of Resnick. Okay, and just sort of some more recent results, people have been studying, the convergence rates, and I'll say a little bit more about this later, by which I mean, depending on some property of this, sort of how far from being separable this entangled state is in some sense, okay? How big does the degree have to be so that we can actually certify it? So there's even quite recent results. I'll talk about one of these in a different context a little later in the talk. Okay, so it's a nice application in quantum information. And I want to go back to one other really classical application. And one of the reasons I want to do this is to say something about a whole piece of the story of this polynomial optimization sum of squares story that I've completely swept under the rug, or completely not discussed at all in this series of talks, and that is really the dual story. So I'm just going to use this as a vehicle to touch on the dual story, but we're not going to say too much about it, just because in some ways I find it much less concrete and more difficult to introduce in a clean and nice way. Okay, so going back to MaxCut. So MaxCut was this optimization problem where I'm trying to, given a graph, I'm trying to partition the vertices into two sets to maximize the number of edges that cross between those two sets of vertices. And we've already seen this polynomial optimization formulation as maximizing a certain quadratic form related to the Laplacian of the graph, subject to these constraints that just tell me that my variables are plus or minus one valued variables. So if we take our kind of SOS-based formalism to give me relaxations or bounds on this problem, that we saw in yesterday's talk, what it would tell us to do. Okay, we've just got equality constraints, so it would say, okay, to get a bound, I need to fix the degree of some polynomials, one for each of the equality constraints, and I'm going to try to minimize the bound I get, minimize gamma, so that gamma minus my objective function plus something that vanishes on the constraint set, okay, is a sum of squares. And again, really the knob I have is to control the degree of these multipliers. All right. Okay, and so it turns out that already choosing degree 0 multipliers, so just scalars, okay, so just having an optimization problem where the lambda i's are just scalars, okay, gives the dual of what I'll call the standard semi-definite relaxation of this problem, okay, and I'll talk more about that on the next slide. Okay, but somehow already just doing the simplest possible bound here will turn out to be quite an interesting non-trivial bound that you get. And in principle, you can choose higher degree multipliers here and get tighter and tighter bounds on these problems. Okay. One of the really interesting things about this particular problem is that we can say something about the quality of this bound, right? And this is something that Andrew asked about on Monday. And I sort of said that in many cases, it's quite difficult to assess the quality of the bounds you get from this. Okay, but people have studied this a lot, particularly in the context of these combinatorial problems. Okay, because it's really connects to the whole world of studying approximation algorithms from the algorithmic algorithms and complexity community. Okay, so if we ignore the top part of the slide for a second, okay, I just want you to look down here at the bottom part of the slide. What turns out to be true is that the bound you get from this relaxation on the previous slide, the way we wrote it, whatever number you compute, okay, it's always an upper bound on the optimum because we're maximizing. And remember, the whole game is to provide these non-trivial bounds that when you're maximizing, you get upper bounds. When you're minimizing, you get lower bounds. So it's an upper bound, but also it's not too bad of an upper bound. Okay, it turns out to be within about 88% of optimality always. So for any graph, in fact, for any weighted graph, you get this bound will be within kind of some constant factor of being optimal. Okay, and this was a big deal when people worked this out. I mean, this was not in the context of all this SOS stuff, but really kind of in the context of this vanilla relaxation, people kind of came to this. It was a big deal because before this, the only approximation algorithm people knew for this problem was a factor 1/2 approximation. And it's very easy to get a factor 1/2 approximation algorithm. You just randomly partition the vertices, and with good probability, that will give you a factor 1/2 approximation. Okay, so this is really kind of the only, just about the only interesting approximation algorithm for this property. Okay, moreover, okay, even though we know that we've got this whole hierarchy of optimization problems we could solve to get better and better bounds, in the worst case, there are conjectures that in the worst case, you actually can't hope to do better than this simplest SOS-based bound, right? So in some instances, you'll definitely do better. But if you take the kind of the worst case point of view, and you assume some complexity theoretic assumption that I don't understand super well, then there's a conjecture that this is really about the best you can do. So it's kind of an interesting situation where although we have this hierarchy of bounds, kind of in the worst case, it may be the case that the zeroth, the very first bound is actually, as good as possible in the worst case. All right. So I want to just finish the discussion of MaxCut by saying a little bit about the dual picture. So all the time, the way we've been thinking has been, okay, the dual, maybe the second dual picture. The way we've been thinking is polynomial optimization, try to find global balance, which in some ways is a dual picture. Okay, for those who think about optimization, it's a bit like Lagrangian duality, what we've been doing. The dual of the sum of squares story, okay, is sort of like taking the dual twice, and it's really like convexifying in some sense our original variables. So what's the story? We've got our polynomial optimization problem. I've written it a little bit differently, so I've just taken the matrix of the quadratic form here. Okay, and I'm just going to do a trivial reformulation first. Okay, so instead of maximizing over little x variables, okay, where the objective function is quadratic, I'm just going to define a new variable capital X, okay, and ask for that capital X to be just the outer product of some binary vectors, okay? So then I'll be optimizing a linear function over a set. And if I optimize a linear function over a set, that's the same as optimizing the linear function over the convex hull of the set. And this is really the second duality bit coming in. So an exact reformulation is to maximize this linear function now, where the big X variable is in the convex hull of all the products of xi, xj's, so that were feasible for the original hard problem. Okay, so I really haven't done anything here, just reframe things. So what's the most natural first relaxation you could come to? And that is to just say, okay, I'm going to consider symmetric matrices X that are in the convex hull of XX transpose, where X is a binary vector. And I'm just going to write down the obvious constraints that are satisfied by this. Okay. And what are the obvious constraints? Well, it's a convex hull of things of the form XX transpose, so these have to be positive semi-definite matrices. And because the variables have to satisfy xi squared equals 1, the diagonal entries of anything of the form XX transpose have to be 1. And so this will survive, this linear constraint will survive, okay? And so this is the standard SDP relaxation of MaxCut, and it is dual to the thing we wrote on the previous slide with degree 0 multipliers. Okay. So just to say something about how do you go higher in this hierarchy from this dual point of view? Okay, and what I'm saying here is really is kind of the dual story, but I'm not going to go into the details about why that's true. So how do you do a higher order reformulation? Well, you look at this and you say, well, I wrote down some constraints that are satisfied by the convex hull of outer product of binary vectors, but I didn't really write down all. This is definitely a relaxation, and there's kind of higher order interactions, okay, that I've lost track of here. Okay, and so what do? Is we say, okay, I'm going to think about again maximizing a linear functional over a set. Okay, and again I'm going to think about a matrix Z, and my matrix Z is not going to be just the convex hull of rank 1 binary vectors, but what I'm going to do is think about monomials of degree D in my binary vector times monomials of degree D in my binary vector transpose. That's some big, crazy, huge thing that has my original rank 1 binary things in the corner. Okay. All right. And I'm going to think about trying to write down, obvious constraints that are satisfied by these much bigger, what we call moment matrices. Okay. By these much bigger matrices. Okay. So these are, so another way to phrase it is that these are all the moments or probability measures that are supported on the constraint set on binary vectors. Okay, that's the moments language. Okay, so what I'm going to do is try to write down all the obvious constraints I can write down on this bigger object, and then just use the top corner of this object in my objective function. Okay, because that corresponds to the xi times xj terms. And so what does that look like? Well, again, I've written something that's the convex at the outer product of two vectors and take the convex hull. So these matrices, these huge things should all be PSD. And the kind of linear constraints you'll see among the entries are, for example, constraints like this. So if you think about the entry that's indexed by the monomial x1 times x2, and then the entry that's indexed by the monomial x2 times x3, okay? If these really were coming from binary vectors, okay, x1 times x2 times x2 times x3 equals x1 times x3. Okay, the x2s cancel because these are plus or minus 1 valued things. And so when I think about these moment variables, the entry of this big matrix indexed by 1, 2, and 2, 3 should be equal to the entry that's indexed by 1, 3. Okay, so you can play this game all through, kind of using this constraint, okay, as much as you can, and you can get a bunch of linear equations that this thing should satisfy. All right, and this is, you're writing down more conditions, more consistency conditions than we wrote down before, okay? And so you get a tighter relaxation. And this really is kind of the dual to the sum of squares relaxation that we did with higher order multipliers. Okay. All right. So I just wanted to mention this so that you got a flavor of what's going on in the dual story. And really, like, this dual story is very, very well developed, largely by Lasserre and many other authors, just as much as the sum of squares story is developed. It's very beautiful, but just I decided not to emphasize it so much in the sequence of talks. Okay, so let's now go on to some more recent research directions related to polynomial non-negativity and sums of squares and so on. This is, again, a very biased sort of subsample of what's been going on. All right, so one, I think, interesting area which has been difficult, but people are starting to get some interesting results in, is really to get convergence rates. Okay, so this is, again, going back to a question of Andrew's from Monday. So we've got these very general way to construct semi-definite programming based, bounds on polynomial optimization problems. But how good are these bounds? I mean, how fast do they converge and so on and so forth? Of course, in general, this is super hard to make any progress on. Okay, and I guess I want to make 2 points. If you give me a concrete problem and I go and get my bound, and we somehow produce a decent feasible point by doing a gradient descent or something, I can assess this bound by looking at the feasible point and looking at the gap between them. Okay, so a posteriori, I can always kind of, on a given instance, if I can produce a feasible point, I can always get some kind of sandwiching of the optimal value. And this might be good, it might not be good, but I could find out that I've done really well in that specific instance, and that's fine. But from the point of view of theorems, what we really want is kind of a priori results. We want to say for this class of problems, it's always true that these bounds converge at a certain rate. Okay, and in general, this is, it's kind of super difficult, it seems. But there are some interesting results emerging, at least in some special cases. Okay, so I just want to give you two such pretty recent results that that now we have the tools to at least understand the informal statements of these. Okay, so one example is due to Monique Laurent and Lucas Slot, and this is about polynomials that are on the hypercube. Okay, so on -1, 1 to the n. So again, a very concrete, very simple, feasible region. Okay. And so what this says is that if you take a non-negative polynomial on the hypercube and you add a little bit to it, okay, so this makes it strictly positive. This is effectively capturing its minimum value on the hypercube. Okay. Then you can certify the non-negativity of this thing using a Schrödinger type positive Stellensatz. Okay. Using polynomials of degree that go like the minimum value to the power -1/2. Okay. And so what's interesting about this result is really the -1/2. So this is a better rate than kind of generic results about degree bounds would give you. And it really somehow exploits sort of some special structure in this constraint set. Okay. And so this is really saying that these bounds do something non-trivial, and it's kind of interesting result to be able to get this. Another result that's actually in some ways very similar. I mean, very similar in terms of somehow the rate that you end up, it's phrased in a different way. Here's a result of Kun Fang and Hamza Fauzi. Okay. And this is about homogeneous polynomials on the sphere. Okay. And we talked about, homogeneous polynomials. It's kind of natural to think about optimization on the sphere. Okay. And here we've got, again, degree 2D and n variables. And there's parameters in this statement where there's parameterized by the minimum and the maximum value of this polynomial on the sphere. Okay. And so what this result says is that if I take kind of the natural SOS relaxation of degree R, okay, and I look at the bound on the maximum that I get. Okay, so I've got the true maximum, and then PR is bigger than the true maximum. Okay, this result gives you a bound on the relative error. Okay, so what's the relative error? It's the bound that I got on the maximum minus the minimum, divided by the true maximum minus the minimum. So this is always at least 1. And what this result says is that as you increase the degree of the polynomials, okay, that you're using for in the certificates, then the error, the relative error, goes like 1 plus, the number of variables over the degree squared. Okay, so again, as you crank up the degree, you don't just go like 1 over the degree, but 1 over the degree squared. So you get this extra factor, and it's kind of the same factor of this 1/2 that's going on here. Okay, just sort of showing up in a different way. The way people prove these sort of results is really by using kind of approximation theory techniques. So using kind of, at some level, the story is that you should show that, you can approximate the Dirac delta by a sum of squares of good degree, somehow of like, it's understanding how well you can approximate the Dirac delta with a sum of squares, and then kind of using that to bootstrapping to understand, polynomial optimization problems. So it's kind of a clever idea. That's really the approach that they take. And this is the result that a more general version of this result is what gave improved bounds on the convergence of the DPS hierarchy for the separable state problem. Okay. All right, so this is kind of some recent results, but you can see that there's a lot of scope to do more. We're really only starting to understand some very simple constraint sets and so on. Okay. All right, so those were positive results. Those are like, this is how things work well. Okay, if you want to get sum of squares bounds that work well, this is how well they converge. There's sort of another school of work that's been going on, and this is much more in the kind of computer science theory, algorithms and complexity community, where people have been really interested in hardness results. So which problems, this is a very powerful, a seemingly very powerful toolkit. Which problems out there are kind of resistant to sum of squares methods? Okay. There's kind of two flavors of this, hard instance type story. One is the kind of worst case flavor where you've got some problem class like max cut, for example, and you want to find, you just need to find one bad instance or one bad family of instances for which kind of maybe low degree sum of squares methods just don't give you anything good as a bound. Okay. Well, it's already not so easy to find one bad problem instance. An even more challenging setting, and it's one where there's been a bunch of really interesting work, is the average case setting. Okay, so this is where you have a problem and you say, okay, even for random instances of this problem, we can show that with high probability, low degree sum of squares methods sort of fail to do anything particularly useful. Okay, so it's kind of even harder to do this because you don't have to just reason about one bad instance, but you've really got to kind of get a high probability statement over a whole lot of instances. Okay, so it's kind of quite a challenging setting. Okay, and what's turned out is that in the vast sort of, I would say 5 years or so, maybe a little bit more, pretty recently, there's been a stream of results, particularly in the average case setting, of negative results for a bunch of problems. So planted clique, and we'll talk about that a bit more in the next slide. Sparse PCA, k-dense subgraph, and constraint satisfaction problems of various sorts. So kind of interesting problems where people have really shown that there's real limitations on what you can achieve with sum of squares methods for these problems. Okay. All right, so let's just go in a little bit more detail about the planted clique problem because it's kind of connects to things we've already talked about. Okay. So what's the story with planted clique? So the idea with planted clique, or one way to think about one formulation of this problem, is that you start with an Erdos-Renyi random graph. So you take n nodes, you connect every pair of nodes with an edge with probability p, and don't connect it with probability 1/2 in this case, and don't connect it otherwise. Okay, so on the left you've got a sample of such a random graph with 12 vertices. Okay, so that's one graph, and then you think about on the other side you've got exactly the same graph, but I'm going to then have a parameter, a clique size, and I'm going to plant a clique in there. Okay, so I'm going to hide a clique in there. I'm going to choose a clique on vertices 1, 2, 3, 4, 5, say, all right? And then I'm going to scramble the vertices. I'm not going to tell you where it is. Okay, and I'm going to ask you to distinguish between these things. Okay, tell me which one has the planted clique and which one is just the random graph without the planted clique. All right, so it's kind of an interesting problem. It's a kind of prototypical average case hardness problem. So what's interesting about it is in a random graph, you can show that with high probability, the largest clique is basically 2 times log n in size, okay, in this random graph. So it's kind of log n size. Okay. But the only efficient algorithms we know for this problem, if I hide a clique in there that has size even a bit smaller than square root of n, all right, these algorithms can't find this. We don't know how to find this with efficient algorithms. So you can sort of plant huge cliques, much bigger than the size of the largest clique in a random graph, and it's very difficult to detect them. All right, and so the question is like whether sum of squares methods can do better than existing algorithms on this. And one way we formalize this is actually to say, well, let's just think about the problem of computing the largest clique in a random graph, or certifying a bound on the size of the largest clique in a random graph, right? Because imagine I could do that. Imagine I could certify a good bound on the largest clique in a random graph that worked with high probability, right? Then if you gave me these two graphs to distinguish, I would try to certify a bound on the largest clique in both of them, right? In the random graph, I'd get my decent bound. And in the other graph, that bound should fail if you're trying to hide a big clique in there, all right? So I would be able to tell. So if I can do a good job of largest clique in random graphs, then I can distinguish in a non-trivial way, these planted cliques. I can find these planted cliques, or at least know that they're there. All right. So what's known about this? Well, sort of, again, fairly recent results on this says that actually, no, sum of squares can't do this. Okay, so natural SOS relaxations, pretty much like the ones we talked about for clique in the last 2 lectures, where you use sort of polynomials of degree d in your sum of squares, fail to certify that random graphs, there's a lot of negatives here, basically can only produce a bound on the size of the largest clique that's like square root n minus a tiny bit in the exponent, okay? And this tiny bit in the exponent is here because if you take the degree up to the size of the clique, okay, then the sum of squares hierarchies compute the largest clique, okay? And so this whole thing should fall apart. Okay, but as long as the degree is like constant, for example, you're really not doing much better than square root of n, for which we already have algorithms to do this. So it's really to say that this is some recent work in really trying to understand really the limitations of sum of squares methods, particularly on random problem instances, which is, quite a challenging set. Okay, so let's, another kind of recent direction is on this average case hardness results for sum of squares. So we've seen like kind of positive results on convergence. These are kind of negative results that say that sum of squares is not that powerful for some problems. Okay, I want to now switch to a slightly different family of problems. This is more, if you like, pure questions about non-negativity and sums of squares, ones that are somewhat close to my heart. So this is a personal choice here. So we've seen a lot about the relationship between non-negativity and sums of squares. Okay, and we've seen that there are certain situations when non-negativity equals sums of squares, but most of the time there are non-negative polynomials that are not sums of squares. Okay, so it turns out that you could also make other assumptions on polynomials that imply non-negativity but are maybe stronger, and ask whether they imply sum of squares. Okay, and one such assumption is to consider convex homogeneous polynomials. All right, so what's a homogeneous polynomial? Just a reminder, it's a polynomial that when I scale the thing inside, the variable inside, that scaling comes out with just the degree, or if you like, it's a polynomial where all the monomials have the same degree. Okay, so what's a convex polynomial? It's just a polynomial that happens to be a convex function, and for because polynomials are continuous, the convex function being convex is just the same as midpoint convexity. Okay, so just if you take the polynomial, you evaluate at the average of 2 points, that's less than or equal to the average of the values of the polynomial. Okay, so it's kind of a bowl-shaped graph. An easy exercise for you to do right now if you're bored is to show that if a polynomial is both homogeneous and convex, then it has to be non-negative. Okay, so this is sort of some condition that implies non-negativity. Okay, all right, and it's a question that goes back, a while now, maybe 10 or 15 years. Well, the original question was to ask, okay, so homogeneous convex polynomials are always non-negative. Are they always sums of squares? Okay, and one of the motivations for this is that sum of squares kind of makes optimization easy in some sense. If you're a sum of squares and your minimum is at 0, which has to be the case here, okay, then SDP-based methods will minimize you. Convexity also makes kind of optimization easy in a completely different way. All right, if you're convex and your minimum is at 0, okay, you could do a descent method potentially and get there. So, are these two notions of being easy for optimization, do they relate to each other in some way? Okay, and so the answer in general is no. Okay, and I just want to summarize for you what's known about this problem, because there's lots of, things that are not known about this problem, even though it's surprisingly easy to state. Okay, so what turns out to be true? Well, if you consider convex homogeneous polynomials in n variables of degree 2d, okay, it's known that if the degree is 2, okay, that convex homogeneous polynomials are sums of squares just because degree 2 non-negative polynomials are sums of squares. Similarly, if I look at homogeneous polynomials in 2 variables, okay, non-negativity implies sums of squares, and so that's why you always get sums of squares along here. Similarly, for homogeneous polynomials that are convex, degree 4 in 3 variables, okay, these are non-negative and hence they're sums of squares by Hilbert's result. All right, so that's kind of what we expect to see. So then in, maybe 10 years ago, Greg Bleckerman showed that once you're bigger than degree 4, so for any degree 2d bigger than 4, there exists a sufficiently large n, okay, such that there is a convex homogeneous polynomial that's not a sum of squares. Right, it's a non-constructive argument, and the ends you get out from this argument are really, really huge, actually, like a gazillion approximately, my estimate. Okay, so that was understood. And then this kind of also amazing result from Bashir al-Qadir, pretty recent result, 2020. It turns out that if you're convex and homogeneous, and you're degree 4 in 4 variables, then you're always a sum of squares. Right, so this is not true in general. If you're a regular old homogeneous polynomial of degree 4 in 4 variables, you may not be a sum of squares. But if you further restrict to the convex such polynomials, they're always sums of squares. It's kind of, I don't know, to me, an amazing result. And it really makes me wonder, where the ticks should be in this picture and where the crosses should be in this picture. Okay. And so what's the other recent results? And, one of the reasons I like this topic is I've actually done something here, is that, is to find an actually explicit example of a convex homogeneous polynomial that's not a sum of squares. And that example is in degree 4 and actually in 272 variables. And I'll tell you why in a second. Okay. But that's really all that we know. We know that these examples should exist in sufficiently large n. Possibly there's an example of degree 4 in 5 variables that's convex, homogeneous, and not a sum of squares. And we also don't know explicit examples in higher degrees. Okay, we know that they exist, but we don't really know what's the smallest number of variables where these examples should exist. Okay, so that's kind of very interesting to try to fill out this table. Okay. So the one more thing I want to say about this, it's really kind of an interlude or another fun example of just sums of squares. But I thought I would be remiss not to talk about non-negative polynomials without talking about the Cauchy-Schwarz inequality. So this is really just a little interlude before we get towards the end. So what's the Cauchy-Schwarz inequality? Well, we all know that it bounds the inner product of two vectors by the norms. Okay, and we can think of this as a polynomial inequality by forming this bi-quadratic form. Okay, so it's degree 2 in x, degree 2 in y, right, and homogeneous. And the Cauchy-Schwarz inequality says that this is a non-negative polynomial. Okay, so let me show you a proof of this just for fun. So we put a proof of something in these 3 lectures. Okay, so why is this? Well, you can think about this polynomial as the determinant of a 2 by 2 matrix, where the top left-hand corner is the norm squared of x, the bottom right-hand corner is the norm squared of y, and the off-diagonal entries are the inner product of x and y. Okay, hopefully you can see that. And then if you know this identity of determinants called the Cauchy-Binet identity, it tells you how to expand the determinant of a product of rectangular matrices. And what you do is you take all the subsets of pairs of columns and corresponding pairs of rows, and you sum up the determinants of the product of those things. Okay, this is Cauchy-Binet. And if you look at Cauchy-Binet, it really shows this is a matrix times its transpose, so the determinant is a square. Okay, and that's really, you get this sum of squares decomposition of the Cauchy-Schwarz polynomial. All right, so that's why Cauchy-Schwarz inequality is the sum of squares. Not the only way to prove this, but I think it's pretty slick. So what's this got to do with the previous slide? Well, a kind of curious fact that I only learned from thinking about this is that the Cauchy-Schwarz inequality actually holds, it holds for real vectors, it holds for complex vectors with a Hermitian inner product. It also holds for vectors with quaternionic entries with the appropriate inner product here, appropriate product, and vectors with octonionic entries, and the appropriate product. So it's kind of crazy that that's true. What's really interesting is that this polynomial is no longer a sum of squares for the quaternionic and the octonionic cases. Okay, and it's really because this Cauchy-Binet identity fails in those cases. It doesn't really make sense. And it turns out that the example, all I'm going to say is that the example of a convex but not sum of squares homogeneous polynomial in 272 variables is really coming from this Cauchy-Schwarz inequality over the octonions with length 17 vectors. Okay, so that's the example. It's kind of crazy, but I really wanted to show you the Cauchy-Schwarz inequality. Okay, so enough of our interlude. The last kind of, I think, recent direction I wanted to say a little bit about that's very connected to sums of squares, although it's not completely obvious at the outset, is the idea of taking a complex set and trying to write it as the feasible region of a semi-definite program. Okay, so what we've seen is that our whole sum of squares toolkit gives us kind of semi-definite programming formulations, approximations, and so on for polynomial optimization problems. But one could ask more generally, like, which optimization problems can you reformulate, using some crazy change of variables and new variables and so on, as semi-definite programs? So how powerful are semi-definite programs? Okay. And one way to formalize that question a bit more carefully is to say, when can the problem of linear optimization over a set, or equivalently over the convex hull of that set, be rewritten as a semi-definite program of some size? Okay, So in particular, what we're interested in here is really taking the convex hull of a set, or if you like, any convex set, and asking whether we can rewrite linear programming over that set as an STP. Okay, so what's the formalism of this question? Well, you say, okay, for which convex set C can I write them as the projection of a spectrohedron, so the feasible region of a semi-definite program? The reason projection is allowed is that if I were optimizing a linear functional over this feasible region here, okay, then I could lift the linear functional upstairs and optimize it upstairs instead, okay, and that would still solve my original problem. All right, so we allow this lifting up to a higher dimensional space, which is very standard in linear programming, usually called extended formulations. Okay, so the question then is, given a convex set, does it or does it not have a description as the projection of an affine slice of the PSD cone, or the projection of a spectrohedron? All right, and this projection is a linear map, a linear projection. Okay, so this kind of abstracts away, it subsumes somehow all the problems that we've been reformulating as STPs, and asks generally, what can we do with this STP toolkit? Okay, I'm going to skip this slide because I don't think we have time, and I'm just going to say, what's the connection to sum of squares, and what's sort of one, really important, somewhat recent result in this area. Okay, so there's a characterization of when a convex set has a spectrohedral lift of some size, and basically it's a characterization through sum of squares. So what it says is, okay, you're going to take the convex hull of a set, and we're going to look at all the linear functionals, okay, that take value at most one on the set. So if you like, the polar of the set, if you know that language. Okay. And so, and basically what it says is that if we can certify the non-negativity of all of these functions on our set script X in some way, then we will be able to unwind that to produce a semi-definite programming, a spectrohedral lift of this set. Okay, so how are we going to certify the non-negativity of these things? Well, what we have to do is we have to produce a d-dimensional subspace of functions on the set. All right, and our linear functional has to agree with a sum of squares of those functions on the set. Okay, so basically, we're going to have a lift of size d if we can find a d-dimensional subspace of functions where every supporting inequality or every defining inequality of the set is a sum of squares of functions in my subspace. Okay, and one important thing about this result is that the functions that appear don't have to be polynomial functions. Okay, in general. All right, so what you can express with spectrohedral lifts is a bit more than sums of squares of polynomials. Okay, that's one of the important things, and one of the reasons why it's challenging to show negative results, to show that you can't construct such lifts. One kind of thing that is true about the functions that appear here is that they're always going to have to be semi-algebraic functions. This is a result of Klaus Scheiderer. Okay, it's really the only structural thing we know about the functions that appear. All right, so we know that these have to be sums of squares of semi-algebraic functions, but definitely not necessarily polynomials. So this takes us beyond sums of squares of polynomials, but it still shows that sums of squares are at the core of what you can express with semi-definite programming. Okay, and Scheiderer used this observation to show the following kind of a result that answered a question that people had been interested in for quite a while. Okay, so people had asked, well, semi-definite programming is pretty powerful. It can do all this crazy, polynomial optimization stuff. Are there actually any convex semi-algebraic, which really means like built out of polynomials, sets that you can't describe with semi-definite programming? Or can you actually get everything with STP? Okay, and what Scheiderer shows, in fact, there exist convex semi-algebraic sets that do not have spectrohedral lifts. And really, I haven't told you the notation here, but really, the example he gave was to take a monomial vector in, I think, 3 variables of degree up to 6, okay, and think about the convex hull of all the monomials you get when you plug in all points in R3 into this monomial vector. That's some convex cone. And he showed that this cannot have a semi-definite programming description, cannot have a spectrohedral lift. And there's been other kind of negative results building on Scheider's result in the subsequent few years, showing other interesting, convex sets that cannot have any semi-definite programming description. All right. So I just want to mention a couple more directions and then I'll wrap up. So this is kind of much more high level again. So I think one of the really exciting areas is people are starting to think very carefully about how do you use the ideas and the philosophy that we talked about in the last couple of lectures to go beyond polynomials, okay? So to use the similar ideas, but how do you make them work in a context where you're not really working with polynomials? And this is, I think, particularly being motivated by problems in information theory. So trying to get bounds on the kind of quantities that usually involve logarithms and entropies and stuff that appear in information theory and on quantum information. And I just want to highlight a couple of directions here. So one is a kind of a whole line of work that Francis Bach has been developing on kind of kernel-based extensions of sum of squares bounds. Okay, so using kind of reproducing kernel Hilbert space ideas, but with the sum of squares philosophy. Another kind of interesting direction by Oisin Faust and Hamza Fauzi has been to kind of try to attack some of these non-polynomial problems via connecting sum of squares with high quality approximations using rational functions. Okay, so kind of rational approximation theory plus sum of squares. Okay. Another direction that I think is really fascinating that I just want to briefly highlight are situations where I don't just want to think about the non-negativity or sum of squares and so on of a single polynomial or a single function, but I've really got a sequence or a family of functions that I want to reason about sort of simultaneously, or I want to reason about some limiting object. Okay, all right, and so I just want to mention two kind of directions in this space. So one that's kind of very interesting has been pioneered by Razbarov and much more recently by Annie Raymond and her co-authors, have been studying inequalities related to things called graph homomorphism densities, which are kind of, you can express a lot of questions in extremal combinatorics in terms of these objects. And using sum of squares, understanding the power and limitations of sum of squares type methods to study these inequalities on graph homomorphism densities. And these are things that, again, they have a kind of notion of limiting graph size appearing. So they're related also to graph forms and so on. Very interesting. I think the other kind of, fascinating thing to me is trying to understand the whole story of non-negativity versus sums of squares and so on for symmetric functions. So in the ring of symmetric functions. Okay, so thinking about symmetric polynomials, I can write kind of polynomial expressions in symmetric polynomials, but then thinking about expressions that make sense when I plug in any number of variables and where the inequality remains true when I plug in any number of variables. Okay, and so one kind of direction here or some work here has been done by Greg Bleckerman and Cordian Rena. I think there's interesting work to be done in that space. Okay, so that's it for me. I just want to point forward towards tomorrow's talk. So tomorrow we'll have Georgina Hall giving the next lecture. And the motivation for her talk is scalability. So we've seen a major challenge is that solving big SDPs is hard, and these tools naturally give us big SDPs. All right, and there's opportunities in this space. A lot of the work is algorithmic, and Georgina will touch on perhaps a little bit of this, but I think she'll focus more on modeling opportunities in this space. So if scalability is a problem with sum of squares based certificates of non-negativity, okay, we should start to explore what are alternative certificates of non-negativity that have good computational advantages over sums of squares, but that we can still develop this kind of formalism with respect to. Okay, that's it from me. Thanks very much for your attention, everybody. It's been a real pleasure giving these talks.
Thank you very much, James. So I guess we probably can afford a few questions. So if you have any question, feel free to either unmute your microphone and ask, or maybe you can type in the chat if you want. Right? So, so is there any questions or comments in here? Right, maybe while people are thinking about it, maybe I can ask some simple questions.
Yeah. Use your chairs.
Right, so
privilege.
It's a bit interesting for me to see the Monique-Lawrence result is actually on Smutchkin, based on Smutchkin kind of representation. So is there any convergence result that related to Putiner one rather than the Smutchkin one?
For that particular example, I'm not sure. I don't know if yeah, I don't know if there's a result. I mean, I think there's probably a result that maybe gives a weaker convergence rate. But I have not studied that in detail to understand this much. Yeah, I mean, yeah, that's a good question. Certainly the other, I mean, the kind of results on the sphere, these ones, don't require multipliers and so on because of the homogeneity. So they're kind of a little bit of different nature, although interesting, they get similar rates. I think the other, hierarchies that people have understood these convergence rates for are these, now I'll get this wrong, but this bounds on the other side from the Lasserre's measure-based, and his other measure-based hierarchy, this kind of one where you solve generalized eigenvalue problems and so on. So there are some convergence rates, I think, kind of on the other side for that hierarchy. I think there's still plenty of work to do. But also, I have to say the disclaimer is that I don't know, all those results super well.
Right. Maybe another quick question is that for your very nice example for this 4 variables and I forget the number,
272.
Yes. So how do we know? I mean, do we know anything between the gap between the 4 variables and the 270?
No.
So nothing is known between these two numbers.
I mean, I would guess that there's ways to reduce that 272 variable instance a bit, like to kind of, but yeah, that was the first explicit example. And I don't think anybody's has found another one. Yeah, it's very disappointing. And so, I mean, I think the challenge is actually that, okay, what's difficult is you need to show something's not a sum of squares. That's fine. You compute a separating hyperplane at some point. The challenge is knowing that it's convex. So how do you make assumptions to ensure that the polynomial is convex if you don't know much about it? And so that's I think where the weakness is certainly in that result. And so I think using a different sufficient condition for convexity than whatever's going on in that work is probably the way to progress.
All right. But thank you. Thanks for this nice example as well. I mean, okay, so maybe we can see whether we have other questions from the audience as well. Let's have a look.
Just a comment, but thank you for the comment, Queenie. Hope some things were understandable, at least. Yeah.
Okay, so
right, everyone's saving their questions for tomorrow, and that's a very good thing to do.
So if there's no more questions, maybe we can please join me to thank James for this very nice talk. Okay, we probably will meet the same time tomorrow, I think.
Yep.
Right. That will be Georgina's talk, I think, if I'm right.
That's correct. Yes.
Okay, so we probably will stop in here, and thanks everyone for sticking around, and thanks for James for the nice talk.
Thanks very much. Okay, see you later, everyone.
See you then.